This might be one of those things. So if you forget something mathematically, like solve the quadratic inequality, you read that and it is like, I have no recollection of my ever doing this in my life before. I have forgotten. You have two options. Option one is just quit altogether and do nothing. Or option two is play around with it a little bit. So we're going to start with option two. I know you guys want to just quit and go home. I would probably get in trouble if I said, we're going to choose option one. Everybody, let's go home. Yeah. If you're just playing around with something, it says, okay, well, if I'm solving, there must be an x value that works. Can you find an x value that works? Can you find an x value that doesn't work? This is a great place to volunteer, because no matter what number you pick, it's going to be one of those two things. So pick a number. 3. So if you tried 3 for x, 3 squared is 9, plus 9 is 18. Does it make it true? Yes. So x equals 3 works. Can someone tell me a number that you could plug in that doesn't work? 6 trillion and 2. So we square 6 trillion and 2, which would give us, oh my goodness, you really mean, it'll give us 36 septillion and 4. And then we add 9 to that, so we have now 36 and 13. Is that less than 25? No. We're just going to round your number down a little bit to 6. And 6 doesn't work. So x can't equal 6. Now, what's the biggest x value that would work? 4. And what's special about when you plug in 4? It equals 25 perfectly. And since there's an equal sign here, that would be allowed. What is the smallest x value that works? Negative 4. Because negative 4 also equals 2. So are you pretty comfortable with saying that the x values that work have to be between, seems to be like they have to be between negative 4 and 4. Seems logical that that would work. And that is the solution to that first one. That is not how you did it in grade 11, but now I'm going to re-show you a method that you learned. You might be like, oh, I remember some of this. And hopefully by seeing the solution already, it'll make sense why we did this method. So the method that you learned in grade 11 is you first solved where they were equal. So if we make them equal, I can move my 9 over, square root both sides, and I would get that plus or minus 4 that we already discovered. With that plus or minus 4, you made a number line. And you put negative 4 on that number line, you put 4 on that number line, and you either did an open circle or a closed circle. Since there's an equal sign, we did a closed circle. For this one, we're going to do an open circle because it's not equal. So you get to color these in. That's part of my day. Because those values are included. And after that, anything in each of these intervals is either going to always be true or always be false. And we already tested, like we tested 3. We know that this area is always true. We tested 6 trillion and 2, thank you. And we found out that happened to just barely be false. We didn't test anything less than negative 4. So you could try negative 10. Negative 10 squared is 100. Plus 9, no, it's false. This section is false as well. And from this number line, we could write that our solution is from negative 4 to 4. You could either write it in interval notation or you could write it in set notation. Another thing that is sometimes helpful with these equations is the following. I like to rearrange the equation. If I rearrange this equation, so that one side is equal to 0, do you say that you would have x squared minus 16? And x squared minus 16 is a parabola that's been moved down 16 units, like that. It happens to have an x-intercept at minus 4 and at positive 4. Looks just like our number line. And what we're really looking at with this inequality with its 0 is we're really looking, where is the parabola? In other words, where are the y values of your parabola less than 0 or below the x-axis? Can you see that it is true in this section, which we labeled as true, and false in the other sections? So there's a little connection of what you partially saw in grade 11. I haven't done any inequality solving for a very long time, and probably legitimately forgot it, but hopefully when you see it again, you're like, oh yeah, I kind of remember doing that a bit. But it makes sense that you'd want to find out where they're equal, and then from there, you can find out which intervals are true or false. And that can be a lot faster than sometimes guessing and checking, because we really did a guess and check kind of method with this first one. This second one looks like, oh, more mental math if I was guessing and checking. But if I solved that one, x squared plus x minus 6, I'd first make it equal to 0. It factors nicely to x plus 3 and x minus 2, so our solutions are x equals negative 3 and x equals 2. I draw my number line, I add negative 3 and 2, and this time, I leave the circles open because the original equation didn't have an equal sign. Because these were the values that made it equal. So leaving the circles open is a reminder for myself, those are not part of the solution. I always like to use 0 as my first test point. Mental math is really pleasant. If you plug in 0, you get 0 plus 0 minus 6. Is minus 6 greater than 0? No. So the middle section here is false. If I try something bigger than 2, like 3, 9 plus 3 minus 6 is 6. This is true. And similarly, if you plug in something less than negative 3, like negative 4, 16 minus 4 minus 6 is 4. This is also true. So we can write our solution. It's true in two places, so you can either write it like this, negative infinity to negative 3, round bracket because it's not included, and then starting again at 2 to infinity. Or you can write it as x is less than negative 3, or x is bigger than 2. And you have to use the word or, not the word and. Because it's happening in this section or in this section. Both are possible. If you use the word and mathematically, it has to happen in both at the same time. It has to be less than negative 3 and bigger than 2 at the same time. And there are no, then that would be like, there's no answer. You have to use, if you're writing it out, you have to use or. They would probably accept the comma on the exam. They're not really super fussy. Just like in this one, if you used or instead of the you, technically that's the proper notation.
Can you use that and then you instead of the or?
Mix the two notations together. I don't know, you'd have to ask the teacher who's marking your exam and be probably really nice to them, and you might have to check.
Can you please use you instead of or?
So these are a little review of grade 11. And it's going to come into effect in questions with compositions of functions like this. So this is a great example. We'll do this one as well. We'll see how this is used and why it comes up every once in a while. So we have the graph of f of x as a square root of 3 minus x, and the graph of g of x which is x squared minus 1. And we want to, they want domain and range of each of these. So if I just draw a quick little graph. Oh no, this is failing. How do you quickly graph 3 minus x? Thank you. I would probably think of it as minus x plus 3. And then I'd have to factor out my negative. Oh my goodness, look at the review that we're doing. Right, because there's a horizontal reflection and horizontal translation. So this is a square root graph. Horizontal reflection, flip the other way, and then move 3 to the right. It would look like this. That's option 1. Option 2, you could have just graphed 3 minus x on the inside and used your square root rules to graph it as well from chapter 2. And the second graph, x squared minus 1, that's easier to graph, would look like this. So, domain and range of this one, x is less than or equal to 3, and range y is bigger than or equal to 0. And for this blue one, the domain is everything, and the range is y is greater than or equal to negative 1. And on your next page, you have the following chart. We want to graph f of g of x. So first of all, you'd have to plug in negative 3 into g of x. And g of x squares at minus 1. You would get 8. 4 minus 1, this will be 3. This will be 0. This will be negative 1. And by symmetry, those are easy to calculate. Then f of g of x. Well, now we would do, since g of negative 3 is 8, we now do f of 8. And if I plug in 8 into my equation, that would be the square root of 3 minus 8, which is equal to the square root of negative 5. Uh-oh. Got a little bit of smoke. That would be bad. That would explode. So when that happens, we just write not possible. However, if I plugged in 3, I'd get the square root of 0. That'll be 0. That's not bad. If I plug in 0, I'd get the square root of 3. Negative 1 would be square root of 4. That's actually 2. And then I've got symmetry again. 3, 0, and not possible. So if I go to graph this, I'm going to have the point at negative 3, it's not possible, but negative 2 is at 0. Negative 1, it's at root 3. At 0, it was at 2. Root 3. So it appears to look like that. That's just based on my table of values and me hoping that I didn't miss any points. So I really extremely feel confident writing my domain and range from a table of values. I'm lying. Usually a table of values doesn't give you extreme confidence, but we're going to go with it. We're going to say my domain goes from negative 2 to 2, and my range goes from 0 to 2. That's what I feel. Okay? Now the question is, how do we do this algebraically so we know that we're right, so that we can feel a little bit better than just sort of like, ooh, I hope I'm right. Because most of us taking pre-calculus class are not very happy with the I hope I'm right kind of strategy. So, So what we have is we're going to write the explicit equation. We're going to find that in everything in this unit, if you can write the explicit equation, usually your life is easy. So we're trying to find f of g of x. We knew that g of x was x squared minus 1. And f was the square root of 3 minus whatever you put in, so it'd be the square root of 3 minus x squared minus 1, which I could simplify. This will be the square root minus x squared, and then this will be 3 plus 1 plus 4. Where does your grade 11 come in? Well, if they asked you to find domain, what are you allowed to square root? Only positive numbers equal or equal to 0. So we know that the inside has to be bigger than or equal to 0. And now we have an inequality to solve. How did we solve those inequalities? We first made them equal. So I'll make it equal. I'll move the x squared over. I get x is equal to plus or minus 2. I draw my number line. Label negative 2, label 2. And since it has the equal sign, I get a color. And now we have to check. Where is it true? Where is it false? I probably start with 0. If I check 0, is 4 bigger than or equal to 0? That is true. If I check 3, does not work. And this negative, if you plug in 3, remember the 3 is getting squared, giving you 9, and then you multiply by the negative out in front to give you negative. And same thing over here, this will be false as well. So our domain is from negative 2 to 2, which we discovered from our table of values is what we hoped would be the right answer, and it is. Yes.
If like the middle part is always true, won't the outside always be false?
For parabolas, yes. But you will get some questions in AP Calculus. You can have graphs which go true, true, false. Think about our first unit. If something has a bounce, it could stay negative, and then go positive. So depending on the function, it doesn't have to alternate. Parabolas, though, will always alternate due to the nature of a parabola. But you could have some functions that don't. So don't just automatically start alternating from now until forever on these. And if you wanted to draw the graph, if you wanted to graph y equals the square root of negative x squared plus 4, it's a little review from chapter 2. How did you graph any square root graph? First, you graph the inside. The inside would be 1, 2, 3, 4. I'll draw it in blue. Parabola, downward facing. This would be my parabola, negative x squared plus 4. Then how do we square root any graph? We found out where the y values were 0 and the y values were 1. Any other nice points? Well, for sure. Could you square root 4? That would be 2. Between 0 and 1, our graph has to be slightly above. And then slightly below. So from our table of values, I thought our graph actually looked pretty good. But this method, we would know, that's exactly what it's supposed to look like. And now I see my domain and I see my range. Okay, let's go to example 1. Most of the examples are easier than this. Most of the examples don't involve square roots, so your life is actually really easy. right, here's f of x in blue, has a y-intercept of 1. Its domain would be everything. Its range would be everything. And here is negative x squared plus 4. I'll do that one in green. Again, its domain is everything. Its range is less than or equal to 4.
Why are you writing that down?
State the domain and range of each function. So I did a quick graph, and unfortunately, the domain and range of the original functions do not help you whatsoever with composition of functions. There is not really anything you can easily say for sure that the domain and range is going to be moving for. What we're going to find out, though, is that if we find the explicit equation, our life is easy. So I have f of g of x. Explicit equation, well, g of x I can replace with 4 minus x squared. And then what does f of x do? It says whatever you put in, if I put in a 4 minus x squared, I just add 1 to it. So this gives me negative x squared plus 5. That's easy to graph using transformations. Domain is everything, but its range is y is less than or equal to 5. I'd like you to try B on your own. I'll put the answer up in a bit. Did you get that f of x was f of, is it x plus 1?
Yes.
And then that becomes x plus 1 plus 1, which is x plus 2. As a graph, domain is everything, and range is everything.
What are questions for this one?
Questions for this one are number 4.